Large language models are highly capable of generating complex code, but they consistently hallucinate software packages. When prompted to configure dependencies, an LLM will frequently output the names of software libraries that simply do not exist. Developers and automated coding agents often copy these generated dependencies directly into import statements or pass them straight to package managers. This immediate, unverified execution creates a direct vector for a severe software supply chain vulnerability known as a package confusion attack. Threat actors actively monitor AI models to see which fake package names they frequently hallucinate. The attackers then create malware packages and register them in real-world databases, like PyPI, under those exact fabricated names. When the LLM recommends the fake package again, the automated agent downloads the attacker's malware. Attempting to solve this by bolting on external verification, like retrieval-augmented generation to cross-reference every package against a database, introduces unacceptable pipeline latency and pipeline complexity. The internal alternative is full model fine-tuning. This requires updating billions of parameters, incurring exorbitant computational costs, and risking severe overfitting to specific output formats, which degrades the model's general coding capabilities. These two inadequate solutions leave a critical vulnerability gap in the modern software supply chain. The defense is either too slow for deployment or too expensive and destructive to the underlying model. Engineers currently balance three incompatible variables. They must accept high latency, pay massive compute costs, or leave automated pipelines exposed to active security threats. A common assumption among engineers is that localized knowledge editing techniques, like ROM or MEMET, can easily patch these hallucinations without the overhead of full fine-tuning. This chart compares full fine-tuning against localized editing methods like ROM and DIN. While the editing methods do reduce hallucinations, they achieve this by suppressing the model's ability to recommend packages entirely. The valid rate metric, the model's capacity to output actual correct packages, plummeted to near zero. This collapse happens because standard knowledge editing is designed to overwrite static one-to-one factual associations. It works for updating a specific subject-object pair, like changing a capital city. Recommending software dependencies is a dynamic, task-conditioned output. A single prompt requires the model to generate multiple valid packages simultaneously, and the correct answers are deeply context-dependent. Correcting hallucinations requires a surgical refinement of the validity boundary between real and fake tokens, rather than a broad overwrite of the model's weight space. To map the LLM's token representation space, the model accurately retrieves valid software packages like CFI or requests, placing them into this probability space. The architectural failure occurs when statistically plausible, hallucinated fakes like ECMWFR are pulled into the exact same cluster. The model relies on an internal mechanism to separate the real tokens from the fakes. We call this the package-validity boundary. When developers input highly specific task descriptions, the contextual routing causes this boundary line to shift, blur, and ultimately fail. Instead of forcing the model to memorize fixed outputs, the engineering objective becomes realigning this exact boundary line within the architecture. Before we can refine this boundary, we have to execute a mathematical search to isolate the exact neural weights responsible for drawing it. We use a strategy called risk-aware module localization to target the specific transformer layers causing the errors. By testing every attention and multi-layer perceptron block across the network, we can determine which specific modules are most sensitive to hallucination triggers. This is the boundary risk score equation. It measures how strongly any given layer promotes hallucinated outputs. The first half extracts the next token logit vectors specifically for the hallucinated package candidates. The second half acts as a valid package anchor term, offsetting the model's preference for fakes. We take this computed risk score and backpropagate it entirely through the frozen base model. The gradient signal interacts with the current weight values inside the matrices, producing a localized saliency score for every module. This generates a heat map of sensitivity across the architecture. We then discard the vast majority of the network, isolating only the absolute top-ranked modules that exert the most control. By mathematically tracing these risk gradients, we locate the exact neural coordinates responsible for package hallucinations, setting the stage for a surgical edit. With the coordinates identified, we inject lightweight, rank 8 LoRA adapters exclusively into these localized modules. This formula represents the tripartite objective function used to train the adapters. The first component is negative log likelihood loss, providing positive supervision to retain valid token generation, which prevents valid rate collapse. The second component is an unlikelihood loss, explicitly penalizing the generation probability of known fake packages. The third component applies Kullback-Leibler divergence for regularization, locking the surrounding intelligence in place to prevent behavioral drift. This simultaneous three-way optimization reshapes the validity boundary, suppressing the fakes, reinforcing the valid packages, and preserving the core intelligence of the large language model. This dashboard tracks the bound framework across 3 models: DeepSeek Coder, Qwen 3, and Llama 3.1. On targeted edit prompts, the package-level hallucination rate drops by nearly 80%. Simultaneously, the valid generation rate actively increases, proving the editing paradox is resolved. When evaluated on entirely unseen prompts, the hallucination rates remain consistently suppressed, confirming the model hasn't simply memorized the training data. The framework also demonstrates cross-task generalization. The edits successfully reduce hallucinations in explicit pip install command generation, a distinct format from standard package recommendations. Generalization to different syntax structures confirms that the edit is logic-based rather than a surface-level response to specific prompt wording. The model maintains a structural distinction between real and fake software ecosystems, regardless of the specific task format. This ablation matrix confirms the necessity of the complex math. If the negative unlikelihood loss is removed, hallucination metrics spike by 274%. If positive supervision is removed, the model's valid package generation collapses by 81%. The editing process produces a microscopic parameter footprint. This massive block is the 14-gigabyte artifact for full fine-tuning. In contrast, the complete localized bound edit requires just 731 kilobytes of data, securing the pipeline with zero external verification latency. By abandoning the idea of factual rewrites and instead mathematically isolating the reality hallucination boundary, we can surgically secure generative code pipelines with an update 20,000 times more efficient than brute force retraining.